Okay. So basically, the longer I go down the hill, the faster I'm going down the hill. The faster I'm going down the hill. So this is going to be a break, if you will, in our talking about linear modeling. Because a linear modeling would say, the further I go down the hill, the longer I go down the hill, I cover the same amount of distance each time. If I go, 25 feet down the hill, or if I go for 20 seconds, I'm going to cover 30 feet. And if I cover 20 more seconds, I'm going to cover 30 more feet. And if I cover 20 more seconds, I'm going to cover 30 more feet. But that's not what's going on here. As you guys realized very early on, in the first few seconds that I was rolling, I was hardly covering anything. I had to get going for a while, and then I was picking up speed. By the time I got to the bottom of the hill, I was actually picking up real speed. So what I want to do now is, I want to actually analyze when we need to talk about linear modeling versus when we need to talk about quadratic modeling. Now, this is not going to be obvious right now. This kind of data is called quadratic data. So linear modeling implies that your data looks something along these lines. Something along these lines, where you've got essentially, and you may have some noise. You may have some noise in the data, but essentially it's heading upward at a constant rate as it heads, or downward. It could be up, it could be down, it could be horizontal for that matter. But the key is that it's consistent. For any change in x, the change in y is consistent. So your change in y over your change in x is consistent. We were calling that grade, we were calling that slope. There's all kinds of things you can call that. But what makes linear data linear is that your change in x and your change in y have this consistent ratio, predictably consistent. And that's fine for lots of things. There are lots of things that operate just that way. But there are other kinds of data, like a bike rolling down a hill or a ball rolling down a hill or something, anything falling on Earth for that matter, that don't have that kind of consistency. One of those, we're going to look at two of those in this class. This week we'll look at quadratic modeling. Next week we'll look at exponential modeling. So that's what we'll talk about today, start talking about today. Swing this over there. Is quadratic modeling. We'll come back to my data here in a second. Quadratic modeling, the data is going to look something, well, it can look something like the bike data here. It can. It doesn't have to. Quadratic data can look, well, you remember from Math 65 and Math 95, parabolas, which quadratics are, either curve upward or they curve downward. It depends on what kind of stuff you're modeling. So in our bike data, the one case is that the data, if you will, trend upward. So in other words, you've got a delta x and a delta y here that has a certain ratio, but then if you look at the data over here, you've got a delta x and a delta y that has a different ratio. It could be increasing if the parabola is going up like this. It could be decreasing if the parabola is going down. We'll look at all these cases as we go through this discussion. So basically, with quadratic modeling, that rate of change of delta y over delta x is not consistent. However, it is still predictable. It is still predictable. And what I want to do is I want to take a break from the bike for a moment, turn the bike data off, and look at a very general quadratic model equation, that's the kind you looked at back in Math 95, maybe 65, depending on who you took it with, and look about what I'm talking about. It's not consistent, but it is predictable. It is predictable. So let's turn this guy off for a moment. Put this up. There we go. Swing this forward. And what I want to do is I want to compare and contrast. Let's do this. I want to compare and contrast a linear model and a quadratic model. Okay? Linear model and a quadratic model. So, a linear model real quick example would be something like y equals 2x. Real simple, y equals 2x. Let's look at some points that satisfy that equation, y equals 2x. Okay? X and y. So what I'm doing is I'm going to keep y consistent, or excuse me, I'm going to keep x consistent. We'll start it simple. We'll start at 0. 0, 1, 2, 3, 4, 5, 6. What are the y values that correspond to those x values? Assuming the equation is y equals 2x. What are the y values? 0, 2, everybody together. 4, 6, 8, 10, 12. Predictable and consistent. So do you see the predictably consistent delta y and delta x? Absolutely. What's the delta x right there? And delta x change in x. So 0 to 1 goes up, changes by 1, goes up 1, a plus, you can put a plus 1 there. 1 to 2, plus 1. 2 to 3, plus 1. Predictable. Predictable, consistent. And how about the change in y over each of those changes in x? 0 to 2, up 2, 2 to 4, 4 to 6, predictable, consistent, happy. And we defined the slope of this line to be 2, because the change in y over the change in x is 2. You see it there, and you see it here. For every 1 x in the run, you get 2 y's in the rise. Yeah, I guess that rhymes and it's correct. So your slope, or your grade, or your delta y over delta x, or your change in y over change in x, however, I mean, there's a whole bunch of different ways, and depending on who you took 65 with or 60 with, you're going to do it any of these different ways, it's always going to be 2 over 1. Even if you choose to not look at it sequentially. Suppose you go all the way from 0 to 2. All the way from 0 to 2, you pick up 2 x's. But all the way from 0 to 2, that means you go all the way from 0 to 4, which means you pick up 4 y's. 4 y's to 2 x's is 2. It's the same as 2 over 1. So 2 over 1, 4 over 2. If you want, you can look at the entire realm, which is 12 over 6. It's all 2. It's all predictable. It's all consistent. It's all 2, which ties back to the slope up there of 2x. And that's kind of what makes linear linear. It ties into this image of the data over here, in that this predictably follows or consistently follows from this. So no matter where you draw points on this data, all those triangles are going to have the exact same shape. Different sizes, they'll be blown up or shrunken down of each other, but they all have the exact same size and shape. Excuse me, same shape, different sizes. But they all have a rise, a grade of 2, in this case, a grade of 2. And that's linear modeling. We spent all last week talking about linear modeling. Now let's talk about some quadratic models. Let me erase this part right here, because this is the kind of the image I want to contrast it with. Let's pick a nice quadratic equation. What do you guys think? And keep it simple. For starters, the bike's going to get complex pretty quickly, which is nice, actually. How about y equals x squared? Let's go quadratic. Let's make a chart for y equals x squared. Use the same x values. 0, 1, 2, 3, 4, 5, 6. Why do these lights keep going off? It's dark as hell outside right now. There we go. So, notice we get the exact same changes in x. Plus 1, plus 1, excuse me. Plus 1, plus 1, plus 1, plus 1. Beautiful. So, it starts the same as this one over here. Let's do the y values for that one. If x is 0, what's y in this one? 0. 0 squared is 0. 1, 2, 3, 4, 5, 6. Okay, friends. So there are the squares of the inputs. This is what makes it quadratic, squaring the inputs. Let's look at the changes in y based on those changes of x. So from 0 to 1, it's up 1. From 1 to 4, it's up 3. From 4 to 9, it's up 5. From 9 to 16, it's up 7. From 16 to 25, it's up 9. And from 25 to 36, it's up 11, which means we don't have the consistent rise and run like we did with linear. But is it predictable?
Yes.
It's definitely predictable, isn't it?
Yeah.
How is it predictable? What are you seeing that's predictable about it? What are you seeing? Jake, what do you see that's predictable?
It's the last number. It's the last number difference plus 1, plus 2.
Okay, so if we knew the last numbered difference back here, so 1, 3, 5, 7, 9, those are odd numbers in sequence. The next one up, well, it would be 7, right? It would be 7 over here. Now, we know that 7 squared is 49. But if we didn't know that, we would know that the next number up would have to be 13 more than this one. And 13 more than 36 is 49. Hot damn. And that's cool. That's pretty cool. The problem is, what if you needed the 100th number? That's when it gets annoying. But that's okay, that's what we have technology for. So what I want to do is, I want to analyze my statement that it's not consistent, but it is predictable. What's the difference in this difference?
2.
It's plus 2, isn't it? How about the difference in that difference?
2.
There is the predictability. This is essentially what Jake just said. Each next difference is 2 more than the previous. So essentially, what you want to kind of take away from this, and we'll explore this more in your homeworks, it's kind of cool. What you want to take away from this is, when you have linear data, the first differences are constant. And when I say the first differences would be this set of carets that are right here. When the x carets are the same, 1, 1, 1, or 2, 2, 2, or 3, 3, 3, it doesn't matter to me which interval you use, 1's the easiest. When these guys are consistent, the first differences are consistent. That's what makes linear data linear data. That's what makes slopes happen and slopes be consistent, is because you have consistent first differences. That's what you're kind of looking at right here. These are your first differences right here. So that's a quick way of identifying, and I think your textbook talks about this. It talked about it in the last bit. Quadratic does not have consistent first differences, but it has consistent, what do you think? Second differences. That's what quadratic has. Quadratic data has second differences. Second differences are consistent or constant.
Oh, can that be forever? I mean, that's for, can that be a rule? It doesn't change?
Yes.
One of those things?
Yeah, and you're going to prove why in your homework. You're going to actually look at why this has to be this way. Now, this is a perfect equation of y equals x squared. When you're dealing with real data, it tends to get a little bit messy. So it's going to be approximately equal. We'll deal with that as we go through the class too. Yeah, but this is by definition your first differences, these are your first differences. The first differences don't have that. The first differences, no. But the second differences are constant. As a matter of fact, I can tell you this, on your first part, the first couple questions of your in-class exam next week, I'm going to give you 2 data sets. I'm going to say which one is linear and which one is quadratic. And you're going to base it off of this argument. You're going to do these kind of differences and be like, oh, this one's constant in the first difference, so that's linear. This one I have to go out to the second difference to find consistency, so it's going to be quadratic. What's cool is it expands. If you have cubic data, you have to go out to your third differences. Now the third differences here are 0. If you go out from 2 to 2, it's 0. From 2 to 2, it's 0. It gets boring. But cubic data would actually go out 1 more. Quartic will go out 1 more than that. And it gets fun, but fun is a loosely defined term. I think it's funny. So anyway, we'll focus on the quadratic versus the linear. So that's, if you will, what makes quadratic data quadratic, is that second difference consistency. So when I said that the data is inconsistent in slope but predictable, it's because of this. It's because of this. Now I want to show you something that I want to get your take on it. I'm going to put it right over here. So you guys learned back in somewhere that when you have linear relationships, the most common form of the equation to use is y equals mx plus b, or ax plus b, if you're looking at the TI's version, which I like even better. There was another version of that was called point slope, the point slope version. And essentially what that was something like this. It was like y minus h equals m times x minus k, or something like that, something along those lines. So you had two y values. I think the h and the k were interchanged. It doesn't matter. Maybe you used y1. Let's do this. This might make it easier for you to see. x1. We'll look at something like that. This is point slope. So you got a slope and you got a point. So if you solve this for m, you end up looking at this. And that's essentially what a slope is. Change in y over change in x. Okay, essentially that's what a slope is a change in y over change in x. So basically, this form of the equation right here is just a restatement of that slope idea. Don't memorize this. This is something you've seen before. I'm trying to show you why the second difference shows up. I think this will make a connection to that idea, that rule. Okay. Now for quadratic data, or for a quadratic equation, the most commonly used for quadratic, basically on quadratic, is y equals ax squared plus bx plus c. If this doesn't ring a bell for you, don't worry, we'll deal with it in about 10 minutes. If that doesn't ring a bell from previous math classes. And it might not. It's okay if it doesn't. Well, like I said, we'll deal with it. An alternate form of this equation is called the vertex form, which looks like this. I actually have you guys play with it in your project that you're turning in on Thursday. Y equals a times x minus h, whole thing squared, plus k. That's okay, but then you played with it and you did, exactly. If you solve this for a, you get y minus k over x minus h squared. Now, if you look at that little bit there, if you look at that and compare it to this, and you know what, let's make it even nicer. Let's call the slope a, just to keep some consistency in variables over here. And you know what, let's make it even nicer. Let's call this y1, and let's call this x1. What's the only difference between that one and this one?
Bottom squared.
The bottom over there, the x minus x1 is squared. There is your tie-in in the difference in slope between a parabola and a line. In a line, the top and the bottom are both to the first power. So you've got a consistent and constant change in y over change in x. The difference in a parabola is the relationship in the denominator. That change in x is going to be squared, which correlates to that second difference being consistent in the table of values there. If it was cubic, it would be x minus x1 cubed, and so forth and so on and so forth and so on. So that's a cool little algebraic kind of happenstance. That's why. Again, to answer, tell me your name one more time, my friend.
Jake.
No, not Jake. Next to Jake.
Tiffany.
Tiffany, right. You said, is that always the case? Is that always the case? Yes, and that's kind of why it's always the case. It's a function of the function, if you will. It's because the function is set up the way it is. Please.
I'm sorry, I missed something here. Are you substituting the k for the y1?
All I was doing was renaming it, changing its name. Okay. Rather than calling it k, just call, all the k is a y value. Okay. So I just called it y1 to give it this, to make it look like this.
That's what I thought. I just wanted to make sure.
No, I wasn't like hand waving like, oh, I'm just gonna make this y1. Yeah. Let's just call it the same thing as the other one. Okay. Since we're calling this one y1 and x1, let's just call that one y1 and x1.
Sounds good.
Yeah, all we're doing is changing names. That's all. Fair?
Yeah,
so,
I get it now. I just see H and K, and then all of a sudden.
Absolutely, and I suddenly realized that
wait, they might not. You did that.
No, it's okay. And I realized they might not see the point I'm trying to make unless I call everything kind of the same letter. Yeah. And everything's the same except for the power of the denominator, and that's all it takes to take a line that goes like this and turn it into a parabola that looks like this. Is that squared? If you cube it, it then looks like this, and if you fourth it, it then looks like this, and if you fifth it, it then looks like this, and if you sixth it, it then looks like this, and as you change that power on the denominator, I wish that was videoed, oh well.
That was good.
As you change the power on that denominator, the curve just keeps changing. It goes up. And what's cool is there are powers between those. We'll study those in about 3 weeks. There's 1.5 powers, and 2.5 powers, and 3.5 powers. And all it does, it's intermediate changes between, say, a line and a parabola. It's all these cool intermediate steps and changes. But I'm seeing lots of yawns and glazed looks, and the damn lights went down again. So let's take 5. Go flush the carbon dioxide from your minds. We'll come back and apply this to the bike. We'll come back and apply this to the bike.